Okay, last week we talked about kind of the elements of horizontal curves and how to calculate the geometry and the stationing. And now we're going to talk about, or we're going to look at horizontal curve layout. So the textbook calls this method the long chord layout. And the long chord layout is the most common when you're calculating horizontal curve stakeout data, and it only requires one setup, and it assumes that the instrument is at the PC, and I put a traditional horizontal curve diagram back up here for reference. And remember, the PC is the point of your curvature. You have your incoming tangent, or your back tangent, I guess. You have your arc distance along the curve, and then you have your outgoing tangent, or your forward tangent, and you're ending your curve at the PT, the point of tangency. Right? So this long chord layout involves setting the instrument at the PC and backsighting the PI station. So you're essentially taking that straight alignment that you have. Maybe it's a series of centerline stakes from a straight segment of roadway. Maybe it's top back of curb stakes along a long tangent, and now you're needing to stake out the arc of the side of the road for top back of curb. So you're establishing this extension of your incoming tangent, and you're backsighting this PI, because that's where our calculations are going to come from. A couple definitions regarding this this layout method is a station interval, and that's simply the distance along the curve between your required stakes. So that's the arc distance, right? The distance along your arc between the stakeout points that you need to establish. A chord, different than the arc distance, then that's a straight line distance. And in this case, our textbook calls this the long chord method, but I'm going to show you here in a second why I don't really like that name. But just remember, a chord here now means the straight line distance from the PC out to the points along the curve that you need to establish. So it's always that straight line distance, which is inevitably shorter than your arc distance. And then the deflection angle is the angle that you're turning from the PI out to the stakeout point. Right? So your instrument's here at the PC, you're backsighting your PI, you're setting 0, right, for your backsight, and then you're turning a positive angle to the right, and you see these incrementally larger angles here. These are your deflection angles to these station points along this curve. And obviously, it makes sense that the further away you go along the curve from your PC, the larger of a deflection angle you're going to have to turn. The equations to calculate this data, the deflection angle, little d, is equal to 90 divided by pi times the radius. And that's for one, that's the deflection angle to establish a point 1 arc distance, or 1 arc foot away. And then we're going to look at that and how we apply that then to the different lengths of our stationing. But we'll come back to this equation. And then the long chord, little l subscript c, is equal to 2 times the radius times the sine of the deflection angle for whichever chord it is that you're computing at the time. So right, if we're going to be staking points along this arc, every station is going to have its own chord and its own deflection angle. Now, I don't really like the fact that they call this the long chord layout, and here's why. The textbook throws some other definitions our way. They call this the short chord dimension, the individual straight line distance between neighboring points along your curve. So as they're showing in this diagram from the textbook, to establish 50-foot arc lengths, stationing along this curve, right? Station 12 plus 50 up here to station 13 plus a pair. It has a 49.97 foot straight line short chord distance. They call the long chord the individual distances from the PC out to each one of these. And I just threw one as an example here, this green line from the PC out to station 13 plus 50. They're calling that the long chord distance to establish station 13 plus 50. So every one of these stations also has its own long chord distance as well. But if you remember from last week, we actually already applied that name to a geometry on the curve. You can see it right up here, the LC. That's your capital L, capital C, long chord distance of your overall horizontal curve. So I would rather this would just be called the chord layout maybe, or something different than long chord layout. I don't like the fact that there's two ways, or two things being described by the same word here. But just keep that in mind as we go through these calculations. The other thing to mention here is that this is the most common way to calculate horizontal curve layout. It's one setup instrument at the PC, but there are other means. You know, if this is a long horizontal curve with maybe a 2, 3, 4,000 foot radius distance, right? So this is a high-speed curve designed to accommodate interstate travel at 70, 80 miles an hour. It's not likely you're going to be able to see from the PC two distances along this curve if it's that large. There's going to be some topographic change that creates some visual obstructions. There might even be some features that are in the way, vegetation or trees or something. So in that case, you would have to move your instrument if you're using total station, right, from your PC out to an individual station point, a point-on curve, a POC, and establish a new backsite. Generally, you're backsighting your PC and then calculating deflection angles or angles to turn to the right out to your remaining stations along the way here. In all honesty, you'll never do that, and you're not likely even really to do this long chord layout. You know, with CAD, with coordinates, data collectors, and coordinate geometry, radial stakeout from convenient traverse points around a job site is really how most stakeout is done. But you are learning here another application of horizontal curve geometry, and you will have this in your back pocket in case technology fails you, or you really just need a way to establish points along the curve, maybe with a tape and a compass. And if you have a tape and a compass and you understand this method, you could do this. So let's look at an example. We're going to be given just random data here. Radius of 666 feet. This curve has a delta angle. Remember, our textbook calls this I for internal angle, but everywhere else you're going to see this is going to be called delta. 37 degrees, and the PI station is 7 plus 14.39. And we're going to work through the calculations to determine your PC and your PT stations, and then also the stakeout data for points along the curve at every half station. And your stakeout data is your deflection angle and your chord distance for each point. And remember, a station's 100 feet, so every half station is going to be every 50 feet. And this is 50 arc feet along your curve. This is the procedure shown in our textbook, and I'm going to deviate from this just a little bit. I'm really not going to do step 8 here, so I'm going to have 1 through 8 or 1 through 9 of my own steps, basically following this outline. So you're basically going to be able to read along with the textbook and understand this video as well. But I just want you to be aware that I'm going to deviate just a little bit from the steps shown in your book. So my step 1, this is my step 1 for really any problem. Remember I harped on this in soils class. It's always draw a picture and label what you know. And if you draw out your curve, you can establish the PI station that you're given. We know the radius, and we know our delta angle. Step 2, right? We need to solve for the PC and PT stations first. So step 2, we did this last week when we solved for the PC station, is to solve for your T distance, your tangent distance. And if you recall, your tangent is equal to r times the tangent of delta over 2, which is 660 feet, times the tangent function of 37 degrees over 2, or 220.83 feet. And if you know your tangent distance t, like you can see down here in the diagram, we looked at this diagram last week as well. If you know this station, we're working backwards to get back to our PC, so we want to subtract that linear distance to determine the stationing of our PC along the curved alignment. So then step 3 is solve for the PC station. Your PC station is equal the PI that you know minus that tangent distance, or 7 plus 14.39 minus your 220.83, or a PC stationing of a 4 plus 96.56. Step 4 is then we're going forward. Now that we know our PC stationing, we're going to work forward along our curve and calculate the PT stationing. So step 4 means we have to solve for L, which is your total length, and this is the arc length, the curved distance. And remember, L from last week is equal to, this is a constant based on the proportions of a circle when you take into consideration your degree of curvature, right? Degree of curvature was what's the angle required to result in 100 arc distance along the circle out at your arc. So your degree of curvature is kind of a function of your radius, and that proportion resulted in this constant number. So these are just constants. L equals 100 times delta times radius divided by 5729.58. Or in this case, 100 times 37 degrees times 660 radius divided by our constant 5729.58, or an arc distance, total L, of a 426.21 feet. And then step 5 is simply adding that to your PT station, your PC station that you just calculated to get your PT station. So our PT equals where we're starting, the PC, plus your L distance, or 4 plus 93.56, plus our 426.21 for a point of tangent station, our end of curve stationing, 9 plus 19.77. So you're always going to have to do this for your curve stationing. You start here, you work backwards, and you go forwards. Okay, step 6 is determine the arc lengths from the PC out to your desired stakeout points. So now we're on to, I guess, part 2 of our problem. We're starting to calculate the stakeout data. And you want to set up a little table, and I'm going to show you an Excel spreadsheet here in a second that makes this a little easier. But first, we determine the lengths along the arc from the PC to the stakeout points, and we want to go every half station. So you don't just want to jump in 50 feet right away from your first random PC station. You want to determine how many feet it is to get from there out to your nearest whole station. And if we're going from 4 plus 93.56 out to our first whole station would be 5 plus a pair, that's 6.44 feet. And then we're going every half station, and we're going to have nice even stationing along the way. So 5 plus 50, 6 plus a pair, 6 plus 50, and so on, all the way up to 9 plus a pair, and that's our last whole even station before we end at the PT with a random 9 plus 19.77. So after this first random distance to get from our PC out to our nearest whole station, now it's every 50 feet, because this is an arc distance, right? Arc distance along the curve, 56.44, 106.44, every 50 feet along the way up until that last increment where we're going 19.77 feet to get from our even stationing out to the PT. And that distance, 426.21, should check or should agree with the L, the arc length, total arc length that we just calculated to determine our PT stationing, which it does. So now I'm just going to take that data and put it into a spreadsheet, and it's going to make it a little easier for you to see here, and it also makes calculations easier to let Excel start crunching these numbers, because this is all pretty simple math. So you can set up a table that has your station column, your arc length column from your PC, from your PC. This is what we're going to calculate next, is our deflection angle, and then we're going to work through the rest of these. I'll explain them as we go. But we've got our incremental stationing listed, and then the arc length from the PC, or basically from the beginning, listed all the way out to the end. So step 7 is to calculate your deflection angle, little d, for 1 foot. I should say 1 foot. That should be a foot symbol, not a degree symbol. Calculate deflection angle for 1 foot of arc length. And so little d is equal to, or any deflection angle, right, is equal to 90 over pi times radius, or 90 divided by pi times 660, or 0.043059 degrees. And this is a decimal degree form. If you wanted to convert that into degrees, minutes, and seconds, you know how to do that. That would be 0 degrees, 2 minutes, 36 seconds. And what that means is, for an arc of 666 foot radius, if you wanted to establish a point along your arc 1 foot away, 1 arc foot away, you would have to turn the deflection angle 2 minutes 36 seconds. Well, that's not real practical because we don't have any points exactly 1 foot away. But what we do then is simply step 8. Apply this deflection angle to each individual arc length. If we know what the deflection angle is for 1 foot, well, to get 2 feet away, it's this deflection angle times 2. To get 10 feet away, it's this deflection angle times 10. So all we're going to be doing is, just like the table shows here, we're going to take the arc length, we're going to multiply it by the deflection angle to get the individual deflection angles for all of our incremental stations. And that's what it's going to look like. Your little d deflection angle is the same all the way down there. And if you multiply that by your arc length from the PC, that gives you your total deflection angle to establish each one of these stations. And Excel works a lot better in decimal degrees for the trig functions that we're going to do here in a second. There is a script you can run in Excel that will convert decimal degrees automatically into degrees, minutes, and seconds. And I did that here just so we can see what our stakeout data is going to be, because we can turn our tools display measurements in these units, degrees, minutes, seconds, not these units, decimal degrees, even though decimal degrees are a lot more convenient when we're working math. As a check, your last deflection angle should be equal to delta over 2, or 37 degrees over 2, which would be 18 degrees 30 minutes. And it was. And that geometry, let me just go back to our curve. If you remember, from last week, we were looking at these relationships of all the elements of a curve here. Your delta angle is equal to this angle, and the angle from your tangent line down to your long chord is 1/2 that. And this would essentially be, this angle in here would be 1/2 delta, which is also the deflection angle you would need to turn if your instrument is on the PC, you're backsighting the PI, and you're turning a deflection angle to establish the end of your curve, the PT. So that's what we just verified right there. It's always good to give yourself these little checks along the way to make sure you're not making any calculation errors until you get to the very end. So step 9 now is calculate your chord distance for each stakeout point as measured from the PC. Now remember, your chord distance is the straight line distance from the PC out to those points along your curve. And your chord distance is equal to 2 times your radius times the sine of the deflection angle. And I just show that down here in our table. We have the column here of our deflection angles already. If we take the sine of that deflection angle, I just let Excel do that for us, and we multiply that by 2 times the radius, or 2 times 660, that'll give us a distance, a straight line distance in feet for our chord distances. And again, as a check, we know that the last chord distance should be equal to our long chord. Because when you think back to the horizontal curve, the long chord is the overall straight line distance from the PC to the PT. Well, where our instrument's right here at the PC, we're establishing that point, the PT. So we just verified that our deflection angle is equal to 1/2 delta, and now our chord distance should also be equal to the long chord if we calculated it a different way. And last week we learned that the long chord is equal to 2 times the radius times the sine of delta over 2, or 2 times 660 times the sine of 37 over 2. That would equal 418.84 feet, and it does agree. So we did our math right. And then lastly, this is ultimately what you're trying to get for this layout calculation, is final stakeout data. You need 2 pieces of information, right, to stake out a point. You need an angle to turn and a distance to shoot, and that's what you get. Your angle to turn is just called a deflection angle now, and the distance to shoot is just called a chord distance, but it's really no different than the radial stakeout we learned earlier in the semester.